Hey guys, in this video I will be showing you how to create a calibration plot. And what that is we'll take this data right here, which is our dynamic plot, and transform it in order to give us a steady state curve. From this we will find our sensitivity, which is the slope of the line, and our limit of detection. So in order to start, we need concentrations, which we calculated from our mass balance table in the previous video. So we will copy and paste the first three and paste them into here with paste values. And we're only doing 3 steps because, as you see from this data, you have your baseline control right here, and then there's a jump. And whenever there's a jump, that's when you know a drop was added. So about 20 minutes, a drop was added to create this jump, and then you have step 1. And then at 50 minutes, there's another jump. So this is step 2, where there's a jump and it's trying to level off, and then once it levels off, you have your step. So in order to find our average output, we need to find where it levels off. So for the baseline, it's at 20 minutes and a few points behind it. So we'll take the last 5 points. So 20 minutes is right here, and we'll take 5 points. And then we'll do the same thing for the standard deviation. And now we will find the 5 points for step 1, which is right here. So we will take from 50 minutes and go 4 points behind it. So 50 minutes is right here. And we'll do the same thing for standard deviation. And now for our last step, it's just going to be the last 5 points in the data series. So we'll go to the very end of our output, and we'll take these last 5 points. So that is B78 to B82. And then again, the same thing for our standard deviation. And now we want to create a calibration curve for this. So we will take the concentration, average output, insert a chart, and we want to do a scatter plot. And you can click on any of the dots and add a trend line. This way we will have our slope, so we can display our equation and r-squared value on the chart. The r-squared value tells you how good of a fit the line is. The closer to 1, the better. So we have a value of roughly 1 when you round up, but 0.999, which is a very good r-squared value. And so from the chart, we can find our sensitivity based on the slope, which is 25.269. And then our intercept, which we will need in order to calculate the limit of detection, is 2.6378. All right, so now we want to go to our baseline average, and we are just going to input the average at step 0. So this average output right here. Then we need to do the same thing for the baseline standard deviation. Then we will want to perform the 3 sigma method, which is 3 times the standard deviation. And then we will add our baseline to the 3 times standard deviation. So now for the limit of detection, it's going to be the baseline plus the 3 standard deviation minus the intercept, all divided by the sensitivity. And our limit of detection is 0.098033 milligrams per liter, because as you remember, if we go back to our mass balance table, this is what our units are in. So be careful when reporting your units or when converting them to other units that you keep track of them. So that's how you create a calibration plot and find your sensitivity and limit of detection. In the next video, I will show you how we will find the response time by using Solver in Excel.